So shall we start? Am I audible?
Yes, sir.
आवाज आ रही है मेरी?
Yes.
Okay, so we shall in this lecture continue what we did in the previous lecture. We studied this equalizers and co-equalizers. So we move on to continue this and study some more results, discuss some more results in this direction. So the first thing that we want to discuss today is actually this is a new kind of morphisms. They are called as regular monomorphisms. Regular regular monomorphisms. Regular monomorphisms. Okay, so definition. So a morphism from E to A in a category, say small e, in a category in a category is regular monomorphism is regular monomorphism morphism provided that it is an equalizer of some pair of morphisms, provided that it is an equalizer of some pair of morphisms, some pair of morphisms, some pair of morphisms. So regular monomorphism, a morphism is in a category is regular if it is an equalizer of some pair of morphisms. Okay, so recall from our previous knowledge that every regular monomorphism is a monomorphism. Okay, so as a remark, so it follows from one of the previous propositions. It follows from proposition we studied in the last class. So call it star that every regular monomorphism regular monomorphism is a monomorphism, because we have seen that if you have an equalizer for a pair of morphisms, then that morphism is actually a monomorphism. So regular monomorphisms, they are monomorphism, is a monomorphism. But the converse is not true in general. But the converse is not true in general. Okay. because every monomorphism need not be a regular monomorphism. For example, if you take Z to Q, the inclusion, okay, I, it is a monomorphism, is a, because we know that it is an injective, and in set category, or say for example in semigroup category, injectives are precisely monomorphism. So this is monomorphism. It is monomorphism in the category of semigroups. In this category, SGR, that is not regular. That is not regular. Why it is not regular? For if it is regular, for we know that this morphism is also an epimorphism. Okay. Uh, for we know that it is also an epimorphism. Okay. So if it is regular, then it would be equalizer of some pair of morphisms. So if it is regular, then it is equalizer of some pair of morphism, some pair of morphisms. And we proven some equivalent conditions in the last lecture, if you remember, where epimorphisms and if you have a regular mono, if you have an equalizer, and this was the proposition that, so if you remember in the last class we proven this proposition. I will here write the statement of this proposition. If you have E to A equalizer, if it is equalizer of F and G, okay, equalizer of F and G, then these conditions are equivalent. First is that F equals G, second E is an epimorphism, is an EP, third E is an isomorphism, and fourth identity of A is an equalizer of F and G. Identity of A is equalizer of F and, so if this morphism is in, if it is regular, then it is an equalizer of some pair of morphisms F and G. Okay, but since this is also an epimorphism, so it would imply that it is an isomorphism, which is not the case, because in these categories SGR, the a morphism is an isomorphism if and only if it is bijective map, and this is not bijective. This is the inclusion map, so it is not bijective. So if it is if it is so, then this is an equalizer of some pair of morphisms, and thus has, by this proposition, by proposition we had stated in the left side, it must be an isomorphism. It must be an isomorphism, which is not the case, which is not possible because it's an inclusion map, so it cannot be an onto map. So every regular morphism, every regular monomorphism is a monomorphism, but the converse is not true in general. Okay. Now, so what are the regular monomorphisms in some of the well-known categories that we are now going to discuss? First, we will take the set category. So, examples. Examples. So first I take set category. So in set, the regular monomorphisms, the regular monomorphisms are up to isomorphism or up to isomorphism precisely the inclusions of subsets. Precisely the inclusions of subsets. So monomorphisms in set category are up to isomorphism precisely the inclusions of subsets. Sorry, regular monomorphism, not monomorphism. So how we will proceed to just see this? You take any regular monomorphism. So let E to A be a regular monomorphism in set. Okay. So it is a monomorphism in set. So this means it is a monomorphism by our previous remark. This means E is a monomorphism, and in set monomorphisms are also injective, so it means E is also injective. So if it is injective, then you can identify this E with its image via this E. So you have here E to EA to A, where this I is the inclusion map, and you call it as E cap. The whole map is actually from here to here. It is E. Okay, and this E is isomorphic to EA because from E to EA you have the bijection. This E cap is actually a bijection, and this E is isomorphic to EA in set because this E cap is an isomorphism being bijective. Okay.
There is small e, capital E is isomorphic to E.
Oh, sorry. This capital E, capital E, capital E is isomorphic to EA. So up to isomorphism. So E is inclusion. Now, what is our claim? In set, the regular monomorphisms are up to isomorphism, precisely the inclusions of subsets. So here we have done this. Okay, that is, you have now this E cap composition I is E, okay, or you can say that E cap is E because this inclusion does nothing. So E is the inclusion up to isomorphism. Okay, so E is the inclusion up to isomorphism. Now conversely, let you have the inclusion and show that it is the regular monomorphism. Conversely, let
और ये आइसोम ई ऑफ ए आएगा कि ई ऑफ ई कैपिटल ई?
कौन सा, which one?
बीच में जो आपने रखा है ना ई ऑफ ए,
Oh, sorry, it should be capital
ए
E.
आएगा कि ई ऑफ
No,
ई?
no, no, no. It should be EFE. It should be EFE. Yes, yes. It is EFE, not EFA. It is E of E. Now, conversely, let E to A, small e, is inclusion, is an inclusion of a subset, of a subset. Okay. Then uh, I will show that it is somehow in regular monomorphism. So it should equalize a pair of morphisms. So I take, so let so it should equalize a pair of morphisms whose domain is actually A. So let you take A to this set 0 comma 1, a pair of morphisms F and G, where F maps every point of A to 1, where f of A is 1 for all A in A, and G maps precisely the points of E to 1. This is the information about G of G of G of A is 1, but for all A in E, because it is a subset. Then we have so clearly F composition E is G composition E. Okay. Then clearly, then we have first thing that F composition E is clearly G composition E 1. Okay. Then let so you have this here. Now draw this diagram. So from from E to A, you have this E, and from here to this set 0 1, you have two morphisms F and G that we just defined. Okay, so first thing we have seen that in the definition of equalizer, first condition is satisfied. Now choose any E dash, okay, and a morphism, say E dash from here to here, E dash, such that, so let E dash to A, small e dash, such that F composition E dash must is G composition E dash. So I have to get a morphism from here to here, a unique morphism which makes this triangle commute. So I will call it as E bar. So now define E bar from E dash to E with the codomain, just the codomain restriction of E dash, with the codomain restriction. It is unique clearly, and it also makes this diagram commute. Codomain restriction of E dash. That is, actually you are saying that E bar of A equals E dash of A for E dash of A is belonging to E. Okay, so then clearly this E bar is a unique map making this diagram commute. So then
सर ये तो आधे ही सेट पे मैप डिफाइन होगा ना, जिस जगह पे ई डैश ऑफ ए ई में बिलोंग नहीं करेगा, उन पॉइंट्स के लिए क्या होगा ई बार?
है, नहीं हमें वो चाहिए ही नहीं, हमें क्यों चाहिए वो पॉइंट्स, हमें तो ई पे
मतलब मैप तो डिफाइन हम पूरे ही सेट पे करते हैं ना।
मैप तो हम पूरे सेट पे डिफाइन करते हैं।
तो वही है ना, मतलब जहां पर ई डैश ऑफ ए ई में बिलोंग नहीं करेगा जिन पॉइंट्स के लिए, उन पॉइंट्स के लिए क्या होगा?
उन पॉइंट्स के लिए क्या होगा? नहीं वो ये हम इसकी कोडोमेन रिस्ट्रिक्शन ले रहे हैं ना, ठीक है ना, हम इसकी कोडोमेन
यस सर।
रिस्ट्रिक्शन ले रहे हैं, आप नहीं समझ रहे मेरी बात। जहाँ पे वो वही वैल्यू होगी जो ई डैश की उन पॉइंट्स के लिए होगी, है ना।
यस सर।
ई माइनस ई आपके ए माइनस ई पे तो वही वैल्यू रहेगी जो इसकी एक्चुअल वैल्यू होगी, है ना। आपको समझ आ रहा है नहीं?
नहीं सर।
उन पॉइंट्स के लिए भी डिफाइन हो रहा है, लेकिन हमें 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 उनसे गर्ज नहीं है, वो वहाँ पे हम साइलेंट हो रहे हैं, लेकिन वैल्यू वही होगी। डिड यू गेट दिस पॉइंट?
तो मतलब हर एक पॉइंट के लिए वैल्यू ई डैश ए ही आएगा।
हाँ, ठीक है ना, लेकिन हमारा
मतलब
हम यहाँ हमारा कंसर्न यहाँ पे इस ई के साथ है, ठीक है।
यस सर।
हम्म सो e dash of a is e bar of a, and e bar of a is clearly e bar composition I of a. Okay, for all a in e dash. So this triangle commutes and this is unique. So therefore E is an equalizer of f and g. Therefore E is an equalizer of f and g. So we are done. Now in some of the categories you have the if and only if condition, and among those categories there's the categories of vector spaces and group categories where you have, so in the categories, in algebraic categories, for example, if you take these categories of vector spaces, or you take group, all monomorphisms are regular, because regular monomorphisms are monomorphisms, but in semi-group category and ring category we have seen that the converse is not true. But here these categories VAC can group all monomorphisms are regular. All monomorphisms are regular. So we just need to show the converse part that monomorphisms are regular, because regular monomorphisms, they are monomorphisms. This we know. So I will take the case of VAC. You can take the group. The group actually follows from that. So we just need to show that a monomorphism M is a regular monomorphism. A monomorphism M is a, a regular monomorphism. Monomorphism. Okay. So means what? It should be an equalizer of some pair of morphisms. So let from E to E a monomorphism in VAC. So we know that in these categories the monomorphisms are injective maps. This is also true. Now what do you do here? You consider the quotient space. Now here E and A, they are vector spaces over some field, fixed field. Now consider B equals the quotient space A over E of E. The quotient space, and take mappings FG. Take A to B, you take pair of morphisms F and G. F is the zero map, and this G is the natural map. F is the zero map, and G is the natural map. Then if you take F composition of any X, which is F of E of X, okay, uh, and F of E, now F is the zero map, okay, so it sends everything to zero, so it is 0 of B, which is actually your E of A. And if you take G composition E of X, so G of E of X, so G is the natural, it is the quotient, it is the natural map, so it is E of X plus E of E, so again it is E of E, which is 0 of B. So this means F composition E is same as G composition E. Okay, so you have here C, so E to A have E, and A to B you have F and G, such that F composition is G composition E. Now you take some E dash and some morphism here to here, say small e dash, such that F composition e dash is G composition e dash. So let e dash from e dash to A such that F composition e dash is G composition e dash. So since E is, again I will use the fact that it is a monomorphism, so it is injective. So I can just, now since E is mono, this means it is injective. It is injective. Okay. So therefore you have E, which is isomorphic to E of E, and which is subset of A. So where, so you have this situation actually. E is actually um, a composition of an isomorphism and the inclusion. Okay, so you can treat this E as the inclusion. So we can treat E as the, because injective map can be treated as the inclusion, as the inclusion. Okay, so so then if this is the case, then you just take a mapping from here to here, a morphism in fact, E bar, as we did in just in the previous example, as the codomain restriction of E dash, as the, now take E bar from E dash to E as the codomain restriction of E dash. So then clearly this makes this diagram commute, and this is unique. So we are done. Okay, so every monomorphism in these categories is a regular monomorphism. Now I will just leave an exercise for you. You just see this. So exercise, now show that in top the category of topological spaces in their morphisms, the regular monomorphisms are precisely up to isomorphism are precisely up to morphisms the embeddings of subspaces, the embeddings of subtopological space subspaces. Okay, you just have to take, as we have seen in case of set, you have to follow the similar lines, but you have to supply some topology on the to the set 0 1, perhaps the indiscrete topology, to get the result. Okay, now we are going to discuss another class of monomorphisms. They are actually called as extremal monomorphisms. So we have a definition. So a monomorphism a monomorphism M is called an extremal, provided that it satisfies the following extremal condition. Provided that it satisfies the following condition. The following condition. What is the condition? This condition. If M equals F composition E, if it is the composition of two morphisms F and E, where E is an epimorphism, where E is an epimorphism, then E must be an isomorphism. Then E must be an isomorphism. Okay, so you have a monomorphism M, you call it extremal monomorphism. Whenever it is a composition of two morphisms F and E, where E is, so whenever M is F composition E, where the first morphism E is an epimorphism, then it must be an isomorphism. It must be an isomorphism. Now we have a proposition regarding these extremal monomorphisms and regular monomorphisms. It is a sort of link between these two monomorphisms. So let us just state this proposition. Okay. I think we will rejoin and then start this proposition, because only 1 minute is remaining. So let us rejoin back and just start this.